If Australia wants to be a global leader in radiopharmaceuticals, that future is likely going to come down to advanced manufacturing, a section of industry the country still hasn't come to grips with. I'm Rachel Williamson, and this is Phase 3. Only South Australia so far has publicly come out and said, we want Australia's radiopharmaceutical industry to be here. It planted the flag earlier this year by backing a report called From Mines to Medicines. It has the infrastructure, the innovators, and the radioactive mine tailings from which to make the hot new isotopes. But it's up against some heavy hitters. Victoria is the country's biotech hub. New South Wales hosts the country's only nuclear reactor in the Sydney suburb of Lucas Heights. The University of Queensland has the brand new federally funded ARC Research Hub for Advanced Manufacture of Targeted Radiopharmaceuticals. That is a mouthful and more easily known as AMTAR. And Victoria and New South Wales are also where most of the patients are, although perhaps not for long, given the way logistics companies are aiming to bring the medicine to the people, rather than the other way around. People are saying that Australia could have its own mine-to-bench-to-bed radiopharmaceutical industry. Australia has proved it can grow biotechs to global size. The $7 billion Australian Telix Pharmaceuticals is an example of that in the radiopharmaceutical industry. You might remember in episode 2 of this series that I said it was a $6 billion company. Well, its market cap has gone up almost $1 billion since we recorded that interview. Industry bodies have been training new people to work in this industry for some time now, and the country has a strong isotope supply chain thanks to a world-class reactor run by nuclear science agency ANSTO, and a growing number of cyclotrons and generators around the country. But what it's lacking are the precursor ingredients to make some of the more novel isotopes, and a level regulatory playing field for private manufacturers. NTX is one of those companies that is making both isotopes and precursor ingredients. It is making lead-212 from thorium and radium, partly sourced from mining waste in Australia. And it has a top-secret method for extracting the precursor materials needed to make in-demand isotopes lutetium-177 and terbium-161. And if you're keen on this sort of thing, Managing Director Bryn Jones says they're thinking about perhaps listing on the ASX. But I wanted to talk to him about something else. Whether Australia has the it factor needed to go it alone as a radiopharma global hub. And that means being able to make everything from mine, as one report put it, to medicine. I know space is the first frontier for entX, but the second frontier is nuclear medicine with your subsidiary Isomedica. You personally have a background in uranium mining, but you saw radiopharmaceuticals as being a really promising area. Can you tell me why?
I guess as entX, our background is from the mining industry, from the resources industry. Back in 2016, I started talking to our Chief Technology Officer, Julian Kelly, about the sort of growing radiopharmaceutical market and whether we could access some of the sort of what would traditionally be called waste materials from some of these mining operations and really look at where we could secure isotopes of medical value and put them into the emerging supply chains for these types of radioisotopes. So, in particular, I guess what we're focused on at the moment, producing lead-212 and lutetium-177, which is, by far the biggest and fastest growing radiopharmaceutical.
Miners moving into medicine is not as weird a concept as it sounds. After all, mining is just chemistry, and radioactive isotopes are a feature of that work. In fact, Bryn's old boss is the CEO of Energy Fuel, a US rare earths and uranium miner and processor, and they are also moving into medical isotopes. This industry is also turning other companies into miners of sorts. TerraPower in the US wants the waste from spent power station fuel to make thorium and then actinium-225. But Bryn, you are based in South Australia with your Isomedica lab, and that's in the South Australia Health and Medical Research Institute.
Correct. Yeah, the Samry basements. That's right. Yeah, they lock us away 3 levels below ground level when we do our work down there.
How feasible is the idea of an Australian-made supply chain for all of the isotopes that are actually needed in radiopharmaceuticals?
Oh, look, I think entirely possible. I mean, obviously, we're blessed with the natural resources that host some of these materials. We're obviously trying to be ahead of the curve there in terms of responding not only to the market as it could be in 30 years, but responding to the market now and then growing as the market grows, which I think's critical in these sort of radiation handling, because as I said, we're permitting a facility to commercially produce these types of isotopes in South Australia here. But it's certainly not a walk-up start. Is it feasible in South Australia? Absolutely. We have the natural resources up front. We have groups like entX that are more than willing to...
Natural resources like the Olympic Dam uranium mine up in the middle-ish of South Australia, I guess. That's BHP's, isn't it?
Yeah. Olympic Dam amongst others. We have actually some tailings at Port Pirie, which is from historical uranium mining operations that has a lot of this material, and so it's really just about finding that material, finding pathways to extract the value components from those materials, and then getting it into quality environments that can meet the pre-medical sort of qualifications you would need to supply that material into the medical industry.
But you've got that deal with Tailings Holdings as well, the company that runs the Sandy Ridge low-level radioactive waste facility in Western Australia. And it takes a whole range of waste, including mining tailings. And so do you just say to them, sell us all your nuclear waste and we'll turn it into medicine?
Well, so we have a joint developer agreement with Tailings so that they sort of keep an eye on what's coming through their facility. And if there's something that comes across their desk that has a medically valuable sort of component to it, they'll give us a call and say, hey, this is the material, what do you think? And we might collect a sample of that material and put it through our process and say, either yes, that's great material for us, or the economics don't quite work. And so we've got this fantastic sort of mutually beneficial arrangement for effectively looking at some of those waste materials that are coming through their process.
What kinds of rock don't work? What can't you easily get thorium, say, or ytterbium out of?
There's some wastes that are a little bit, a tough nut to crack in terms of the chemistry. Say if you've got a stream that has a high gypsum component, for example, which gypsum is one of those materials that's notoriously hard to leach and to dissolve. So if you had to dissolve a lot of material that had gypsum as its host, that might cost a lot of money. And so you've got to then make an economic determination on whether the money you're throwing at the waste material is going to pay you back in terms of the medical value that you can extract from that material.
I think now is an obvious time to talk about entX's secret technology. You're wanting to make lead-212 and ytterbium-176, the precursor to lutetium-177. How? With what? And why these ones?
Yeah, so two different supply chains there. We might keep on the lead-212 track for now. Where it comes from is effectively the thorium, so naturally occurring thorium, which you quite often find in the rare earth industry. So monazite, bastonite are a couple of rare earth minerals that are commercially processed to make rare earths.
And you're sourcing all of the thorium from Australia?
Australia and Europe at the moment are our two focuses. So we certainly have been working with a number of sources. So when you have that sort of natural thorium, the way radiation decay works, it goes through several steps before it ends up as lead-212, and radium is one of those sort of intermediary steps, and that's really the basis of our technology is to capture and concentrate that radium so that we can then milk a product off of that radium that goes into the lead-212 supply chain.
And what about lutetium? Is that a similar process?
Lutetium effectively is produced by concentrating a particular isotope of ytterbium. Ytterbium has 5 natural isotopes, and what you want to make lutetium is basically you want to concentrate up the ytterbium-176 isotope within that natural ytterbium. And then that ytterbium-176 goes into a nuclear reactor where a small portion of that ytterbium gets made into lutetium by neutron bombardment within the nuclear reactor. Now, obviously, ytterbium in its natural form is non-radioactive. So in this case, we're not really working with radioactivity. What we are doing is manipulating the isotope ratios of that natural ytterbium to concentrate up the ytterbium-176 component.
Here I'm going to call a timeout. There is a reason why entX is keen on ytterbium and why another company in Australia, Silex Systems, is too. All lutetium in Australia has to be made in the Sydney reactor by the Nuclear Tech Agency, ANSTO. But Bryn says Russia supplies 80% of the world's ytterbium-176 feedstock. Russia also supplies most gadolinium, the precursor to the newest sexy isotope terbium-161. entX is also looking at making gadolinium. So let's talk about why Russia is such a big dog. Russia's nuclear agency, Rosatom, has been building the kind of infrastructure needed for medical isotopes since it launched a nuclear industry. The basis of this technology is the calutron. A calutron exploits the tiny mass differences between the different isotopes of ytterbium to physically separate them. Contrast this to the US, which wanted to kill its last calutron in 2002. Russia Hawks blocked that move because it would have made the US completely reliant on their former, and again current, arch-rival for critical isotopes. Proving just how shaky that supply is right now, the US has just banned imports of enriched uranium from Russia. US President Joe Biden signed the bipartisan law in May to put more pressure on Russian leader Vladimir Putin over his war in Ukraine. It's supposed to be just for nuclear power sources, but it's still a reminder that all things nuclear can still be politically radioactive. It also came with $2.7 billion in funding to get companies like entX up and running. Back to Bryn. How are you concentrating ytterbium-176 without being in Russia or owning a calutron?
So we're taking a slightly different tack. It's a bit of a proprietary sort of technology, but we've actually developed an ion exchange resin that will selectively concentrate the ytterbium-176 component, and it works on the different sizes and shapes of the atoms. The platform technology that we've developed for lutetium-177 will be applicable for gadolinium as well. So there'll be a few tweaks we'll have to make to the technology, but effectively the development work that we've done for lutetium will be equally applicable to the gadolinium. Again, what we're seeking to do is displace Russian supply effectively for that precursor, which in this case is gadolinium-160, is supply that gadolinium-160 into, say, ANSTO as a customer long term.
Ion exchange resins are common in water softening. A negatively charged resin bead attracts positively charged minerals in the water. In the case of nuclear isotopes, the resin beads attract ytterbium-176. entX will have a fully operational commercial factory for making isotopes in South Australia by the end of 2025. Lead-212 is the lead product. It conveniently has a 10-hour half-life, so delivery from South Australia to major patient centres in Victoria and New South Wales isn't such a problem. But there is one issue on the horizon that could throw a massive spanner in the works for a growing radiopharmaceutical industry in Australia, let alone South Australia. AUKUS. Bryn, are you concerned at all about the Australia-UK-US military submarine pact leeching talent away from you with high salaries and so forth?
Yeah, it's certainly something that we think about. A lot of the skill sets that we have in-house are skill sets that the AUKUS community in more broadly would want, right? So we've got high radiation competence, we've got great project management skills, we've got all the components that would lend themselves well to that type of environment. The reason we've been so successful in keeping staff is the fascinating work we do. A lot of these people sort of high-performing, intellectually capable people that we employ have really curious minds and want to be active. If you sort of said to those people, well, you can earn 15% more potentially, but you're going to be sitting at a desk doing paperwork, they might think about it, but we like to think that we provide a pretty stimulating work environment, and then some leverage to success of the company as well.
That was entX Managing Director Bryn Jones. He's building a company that builds on mining know-how to move into medical chemistry. And entX is not the only one doing this in Australia. Silex Systems began testing its ytterbium concentrating tech with ANSTO in 2023. These kinds of technologies lay the groundwork for a raw materials supply chain that can feed the isotope makers like ANSTO, which can feed the radiochemists who can deliver drugs and diagnostics to patients. Our following guest is from the next step up in the chain. She is one of the isotope makers.
Hi there, I'm Charis Palmer, producer of Phase 3. When Rachel and I set about building a new podcast for life science leaders, scientists and long-suffering biotech investors, we looked at what was missing in this space. We believe Phase 3 serves an unmet need for in-depth conversations in a world where nuance matters and AI-written investment articles simply won't cut it. If you agree, please follow us and sign up to our newsletter via LinkedIn. Pledge financial support at phase3.buzzsprout.com and rate and review the podcast on the podcast platform you use to help bring it to the attention of others. Now back to the show.
There are some hurdles in the way of Australia building a standalone supply chain of radiopharmaceuticals. We've mentioned the AUKUS nuclear submarine pact. Many fear it will suck talent away from the emerging medical sector. And if Australia were to attempt to build one nuclear power plant, let alone 7, the drag on talent and resources would be even worse. Then there is the fact that Australians haven't traditionally been super keen on nukes in their backyard. Several people warned us not to report anything too scary because of jitters about how Australians might react to the idea of nuclear medicine factories in their local hospitals. But in a country where nuclear power is banned, nuclear medicine is flourishing, corralled by rules from a swathe of different regulators. Dr Jacquie Cawthray is the head of production at Cyclowest and an affiliate investigator with AMTAR. Cyclowest is a brand new cyclotron operator, the second private operator in Australia after Cyclotech, and the only one in Western Australia. It has ambitions northwards into Asia. Jacquie brings deep experience of making isotopes overseas and in Australia. So I asked her, what is the difference between No Nukes Australia and Canada, where she cut her teeth in this industry and with its 19 reactors is much more comfortable with the concept?
So I spent about 12 years in Canada, initially as a postdoc doing radiochemistry over there with Triumph and UBC, and then moved to out in the prairies in the frozen tundra in Saskatchewan, and was at the cyclotron facility there, the Sylvia Fedoric cyclotron facility. That was a GMP licensed facility with Health Canada, but also had a research wing. So the end user, which is really the doctors, that end user was much more involved here in Australia than in Canada. I think even though there was radiopharmaceuticals in Canada and nuclear industry in general is very sort of well accepted industry in Canada, that drive to introduce new radiopharmaceuticals was not as great as what it is here in Australia. Australia really punches above its weight in terms of radiopharmaceuticals globally, and the use of novel radiopharmaceuticals and the ability to try new things in the clinic. So that can only happen if there is a good supply chain. Is an opportunity Australia really has a chance to be a leader. But if we don't kind of address the whole supply chain and therefore the regulatory environment, then it's going to be quite tricky.
To your point about supply, Australia leans on ANSTO, which runs the research reactor in Sydney, And the International Atomic Agency counts 17 cyclotrons here, most of which are in hospitals. Relying on a reactor and hospital-based cyclotrons, what impact does that have on building up an isotope supply chain in this country?
I think the opportunity is there, but as an industry, we need to sort of work together to highlight the supply chain issues and also highlight the need for a more level playing field. So although hospitals may not have the regulatory burden in regards to manufacturing licensing and that, they're also not set up to support industry, like in terms of supporting companies that have clinical trial radiopharmaceuticals. They're there to just produce standard radiopharmaceuticals such as FDG, to produce that for the hospitals for direct use. Whereas companies like Cyclowest are really set up to help support other companies such as Glytherics that are coming through with novel radiopharmaceuticals and help them ensure that they have the correct supply chain that they need to get their radiopharmaceutical into the market, which in the long run benefits the patient.
Cyclowest is an Australian-born cyclotron company, and as of today, when we're talking, you're about 2 weeks out from starting to make your first product, which will be FDG, a glucose sugar combined with fluorine-18. How long has it taken to get to this point?
It's taken Cyclowest from back before it was an empty block of land to a fully functional facility with a TGA license. It has been, I want to say, 4 years in the making. We have designed the building. It's not a normal building construction. There's a lot of things you have to take into account, extra shielding, floor restrictions, and then there's a clean space you have to create as well. Then after that, once the building's done, there's still the equipment install. The validation of all the equipment is quite an extensive task in itself. And then once all that's done, there is also building a quality management system that is required to show that you are in control of your processes. The final step is achieving that manufacturing license from the regulators here in Australia, the TGA. 4 years altogether, which is a long time, but in terms of what has been done, it's probably actually one of the fastest facilities I've worked on to go from nothing to completed.
How many have you worked on?
I've worked on 4, so 3 constructions and 1 already built establishment. Yeah.
What are the regulatory hoops that Cyclowest had to go through in order to get to this point? Because it's a little bit different for you guys as a standalone isotope maker using a cyclotron than it is for, say, a hospital, isn't it?
Yeah, the regulatory sort of environment and framework here in Australia is a little bit different. We fall under the pharmaceutical manufacturing regulations. But at the same time, radiopharmaceuticals are slightly different. We make it, we test it, it's injected and used all within a matter of hours. So the ongoing stability issues that you have with normal pharmaceuticals don't necessarily apply here. So there is some recognition of that with the regulators, and so they've created these exemptions. However, the exemptions aren't across the board. The exemptions apply to manufacturing cyclotrons attached to hospitals. So therefore, a hospital is able to produce and supply to that hospital without having a manufacturing license, whereas Cyclowest, as a standalone manufacturing company, has to apply and receive and comply with the TGA regulations to ensure that we produce a safe product. So even though there is that recognition there that radiopharmaceuticals are not necessarily the same as pharmaceuticals, that recognition does not apply across the board. So therefore, the hurdle for us to become a licensed manufacturing company is much greater than cyclotrons attached to a hospital.
What effect do you think that is going to have on the accessibility of radioisotopes in Australia?
the barrier to us to be a manufacturing facility and commercially supply is much higher than a hospital pharmacy there that has a cyclotron. So therefore, the barrier to us to create and work with companies to produce new radiopharmaceuticals is significantly greater than what it is for a hospital or for anyone falling under the exemption. So therefore, it makes it much harder for us to do that, and therefore access to those new radiopharmaceuticals, any breakthrough radiopharmaceuticals, where their benefits have already been shown, to get them through into clinical trials makes it harder as well.
I'm really keen to understand where the real upside is for a company like Cyclowest. You are still producing an item and then sending it out. So you're not going to see that explosive growth that comes with, say, a drug approval. You're the manufacturer. But pharmaceutical companies in the US in particular are becoming very interested in your sort of company, buying big stakes in them, buying them out entirely. I know you've done that deal with Glytherix. You guys benefit if their drugs work and come through clinical trials. So where is the growth for a company like Cyclowest? Where's the upside for you guys?
If we support companies that have new radiopharmaceuticals and we support them so that they have a supply chain, then they're able to grow. And it's almost like a symbiotic relationship. If they grow, we grow. But then there's also, that's for small companies, but also for much larger companies. Companies like Tailings or Novartis, the supply issues are the same for them. So they really need that supply of isotopes. They need that infrastructure, such as a cyclotron facility. They need that trained team. That's something I haven't mentioned, but to have a team that runs a cyclotron facility, it's a very niche skill set and it's very difficult to find. And so that's not something a big company can just pick up and run with. So with Cyclowest establishing sites just beyond what we have here in Perth, that becomes sort of an interesting growth path just for Cyclowest, but also for other companies because it supports them and their supply chain of radiopharmaceuticals.
Yeah, and if you can do those equity deals where you can actually share in some of the upside from these biotechs and pharmaceuticals companies, then that starts to become very, very interesting. Now, I understand Cyclowest has ambitions northwards to Asia. Can you tell me a little bit about that and why Asia?
So predominantly at the moment, we're making FDG. It has a very short half-life, 2 hours. Every 2 hours, we lose 50% of it. But one of the growing areas for radiopharmaceuticals is radiometals. So their half-lives are a lot longer. So we have the ability to supply further. Radiopharmaceuticals isn't just an industry here in Australia. It's a global industry. So Asia as well is an expanding market. So it makes sense for us to be looking at where we can fit into there and also support the supply chain of radiopharmaceuticals there. You need to make that isotope, especially if it is F18, FDG, you need to have a localized infrastructure. So you need to have that cyclotron locally. We wouldn't be able to ship FDG to Asia from here. We might be able to ship longer half-lives, but they still need that F18 supply chain there locally.
So is Cyclowest looking at sites to set up somewhere in the Asian region?
I think at the moment Cyclowest is exploring opportunities and there are opportunities there, and Asia obviously is a very big market, and it's a market that, like, if we compare it to the US market, the US market is quite full already. So Asia makes sense. It's developing, and there's room there for more players and room there for this supply chain to be completed.
That was Cyclowest Head of Production, Dr Jacquie Cawthray. Australia has some work to do on the regulatory and policy front to create a radiopharmaceutical system that is also geared towards innovation, rather than simply fixing patients. Australia is good at supporting miners and biotechs, and it has some very good hospitals and research organisations. But it's still coming to grips with the return of advanced manufacturing. This is an issue that many industries are grappling with right now, from energy to medtech to defence. In our next episode, we'll switch gears to something that Australia is really excelling at: radiopharmaceutical IP.